All right, so assignment 4 is ready. The deadline is after the Chinese New Year. And good news, no exercise classes this week. This is week 5, very fast, nearly half of the course. And this is week 5 exercise classes. And they will be, we still want to discuss those questions, and they will be discussed next week. Okay, on 18th and 19th. Okay, so this Thursday and Friday you can celebrate your the festival with your friends and family. All right. Okay, some issues, some topics to discuss. Two matters to discuss. Okay, so this is an extract from the note. And basically, I was asked about this question what do I mean by this? Okay. All right. So what I meant by this is if originally you have the number of microstates omega, and after this action, you will have this times 2n. Okay. So this is what I meant. And if you Google, well, this is the usage of language, really. You will see probably different ways to say this. There are even some arguments there. But anyway, the mathematics is clear. Okay, this is what I meant. If you are not sure about how to write it, always give me the mathematics. Okay, so this is what I want. And likewise, you also see this here. It's the same thing. Okay, when I say the number of microstates increase by a factor of x, this is what I meant. Okay, so the student will ask me this question. I hope he's here. Yes. Okay, so this is also consistent with my presentation last time when I talked about the meaning of entropy. So this is one. Another thing I got was something I don't want to repeat again, but I will ask you to watch the video, is what is the logic of this entropy discussion at the end of last lecture about heat capacity. So the question was why this is related to the heat capacity. So now I will explain it again. Okay, so this first sentence here, you can see it as something, you can see as our hypothesis, if you like. According to our understanding of the meaning of entropy, we kind of say entropy can be thought of as the freedom to explore. So this is the concept I like, and this is a concept I mentioned many times. Okay, so if you want to prove that this is consistent with your experience, you can take a piece of solid, warm the solid, and then by doing so, your atoms will have more freedom to explore. It can move more in the configuration space. It can move more in the space you are familiar with. Okay, but with a much smaller length scale. Okay, in this case, we expect warming the solid to increase the entropy. Then the next question is, how do you prove it? Okay, and you can see this as the reverse engineer of the problem. Now, entropy should increase. How do you prove it? You can first look at this. Okay, this both tells you entropy will increase. If you work backward, you know what kind of form you should expect for the heat capacity. Then you measure the heat capacity. That's it. Okay, so if the heat capacity indeed give you an increasing in entropy, then that's it. That is the purpose of this. Okay, so this is one of the question asked, and thank you for all these questions. I appreciate them. You could have asked in the class too. Okay, then I will just fix it right away. The other one, which is deeper, not so much, but the question is, why do we have two terms like this? How do I know we have two terms? The answer to this is this, because this comes from solid state physics. I wrote it down without proving. And indeed, it's not possible to give you the functional form right away. Okay, so this is because I knew the result. Okay, if you really want to know, I will be very brief. I will tell you why you have this form. Okay, this this heat capacity approaching a constant at high temperature limit, this is called the Dulong-Petit result. So here, there's a name, this is called the Dulong-Petit result. Actually, this can be shown by using the equipartition theorem. So from you can be shown using the equipartition theorem. Okay, so here equipartition theorem tells you if you have a quadratic degree of freedom, that degree of freedom will acquire an energy of 1/2 kBT. Does it sound familiar to you? You probably learned it somewhere. If you have 1 degree of freedom, you get 1/2 kBT. No? I really don't want to spend my, come on, give me some feedback. Have you seen this? Okay, good. Now, here, why do you get this constant? The reason you get this constant is because when you look at solid, remember we are talking about solid. When we talk about solid, we have to think about how you keep all these atoms together. Okay, and how do you imagine, how do you interpret this this scenario? You think from chemistry, you know this is the scenario of bonding, and for physics, how do we model these chemical bonds? The way we do that is simply connect the two atoms by spring. Okay, so you have this so-called elastic degree of freedom, and that will give you 1 quadratic degree of freedom and acquire 1/2 kBT. And at the same time, your atoms will move. Okay, so this is simply the question of kinetic energy plus the potential energy, and that will give you some constant times kBT. Okay, and heat capacity is the temperature derivative of that, and that is the you have something proportional to kBT, and if you just take derivative, T will drops. So this is a constant at high temperature. All these modes are activated. Okay, this is for solid. Let me emphasize that this is for solid. If you talk about gas, you have other degrees of freedom coming in. If I have time, I can talk about this a bit more later when we learn more about statistics. Okay, likewise here, I'm very confident that we will be able to discuss this beta T cube term. Okay, this gamma T term, that will be harder, but I want to give you a full scenario. So I will just tell you the reason of this. This is due to the contribution from the conduction electron. Okay, so if you have conduction electrons, that is to say, if in your solid, the electrons are mobile, it will give you this gamma T term. Okay, and in fact, for all these materials I chose here, you have gold, silver, and copper. These are all metals. If you have metals, you have conduction electrons. Sorry, this is not just any electrons. These are the electrons that move. So this is the mobile electrons or conduction electrons in the solid state language, and that will contribute the gamma T term. Okay, and this is linear in T. This is cubic in T, and therefore this term eventually will win. And therefore you see what you see on this screen is mainly the T cube term. So to search for this term, you have to go to very, very low temperature to quench the second term. So you can get this gamma. And once you get this coefficient gamma, you know a lot about the electronic system of your material. Okay? Okay, so this is due to electrons. So naturally, you will ask, what is this? This is again due to the lattice vibration. This spring picture I mentioned. Okay, and this is the mode that is slowly activated, and eventually all of them will be activated, and you reach a constant. And at room temperature, you have this gamma T term, but it's just so much weaker that you don't actually see it. Okay, and this has a name. This is called phonons. So this is the mobile electron. This is phonons. As long as you have a crystal, this phonon term is always there, but these electrons depends on whether you have a metal. Okay, so I think that is enough for, again, for the students who ask this question. Are you here? Okay. All right, and the third matter arising was about this, something I cropped from the chat. Again, is a student here. Everybody, a lot of people saw this question last time. Okay, so the student is here. Okay, now this is my chance to ask you back. What is the problem? What is wrong with this thinking? Actually, this can be very fast. You can answer very, very quickly in Word. Okay, you might want to look at this again. Now, the student. No, okay. Now, there's something else here. What about you look at it in Word? Even if you don't worry about the sign. Suppose you are you just look at the word and analyze it. Now you see, Mr. or Miss Ling Chong, Mr. Chong. Look at this. You analyze the sign, but there's no way to guarantee that the S has to be precisely 0. There's no way to guarantee that plus and minus must cancel. Okay, I appreciate this question very much, and because that allows me to have a chance to reinforce it again. Now, the question here is the following. Where is your reservoir? You do not discuss the reservoir. You have to think about the reservoir, right? So when we talk about reversible heat engine, this heat engine is exchanging heat with reservoir. No? And this is built in everywhere from the derivation since the beginning. Okay, so the role of reservoir is important. This is also emphasized, maybe not strong enough, when I presented the case of isothermal expansion, Joule's expansion in the class last time. Okay, so the role of reservoir is important, right? Because how do we get to the point to discuss everything in the last lecture? Our starting point was Clausius theorem. Clausius theorem. Clausius theorem is actually analyzing a much more complicated cycle than Carnot cycle. Carnot cycle is very simple. You only exchange heat with two reservoirs. Okay, Clausius theorem requires you to exchange heat with many cycle, with many reservoirs, which I call Ti. This I is a running index. So this is the I segment. So I can go to I equals 5, I equals 6. So this reservoir, the role of reservoir is built in. Okay, now if you consider the reservoir, then you understand what's the problem. Now, when you write it this way, you do not really have a closed system, right? Because the reservoir is changing the heat, is exchanging the heat with you. So you do not actually have a closed system. So you cannot say too much about the entropy of the universe. You can at most talk about the entropy of the system, which can go either up or down. Okay, this is what I want to say. Okay, so what's wrong? What is wrong here is this is not, and this is not a thermally isolated system. Mr. Chong, agree? Are you there? Now, in fact, this reversibility is the following. You can think of it this way. We already analyzed the isothermal expansion. So this is in my PV diagram again. Now, this is PV diagram. Now, we know this segment is reversible. This is in the class. I analyzed exactly this problem, isothermal expansion. Okay, we argue that you can, if you just look at the interplay between your system and the reservoir, you can conclude that the total change of entropy for the universe is 0. So this is a reversible process. And in fact, this is the same as the isothermal contraction, right? If this isothermal process is reversible, this is also reversible. And these two are close. Okay, so this is everywhere reversible. So this machine is reversible. Okay, this is already discussed. You can just break it into segments and then discuss it this way. Okay, thank you for all these questions. It's really important for me to get your feedback. Okay, can I move on? All right. Okay, now today we are starting the new lecture. It doesn't mean you can forget, the new chapter. It doesn't mean you can forget the last chapter, because that is something we are coming back again and again to refer to it. Okay, but now, the good thing is this. After today's lecture, suddenly you have a lot of tools in your toolbox, in your thermodynamic toolbox, to analyze your PV system. Because after today's lecture, you have a lot of new equations. Okay, but don't be too concerned. These are here to help you. It will help you to solve problems. It's not, you should not see it as a burden. And at the same time, I would like to emphasize this. I do not expect you to memorize everything. More importantly, I want you to know how to get these equations. There are so many equations. If you memorize it, it's not my favorite way to teach you. Of course, if you have a lot of memory and you want to do that, feel free. But I just want to say, if you learn how to derive them quickly, that is better. Because if you memorize, most likely you get the sign wrong. There's a minus sign here and missing minus sign there, and that is dangerous. Okay. All right. So first, I would like to introduce a few more energy-like quantities, as I already previewed for you last time. Okay. So we want more energy-like quantity. Okay, what do you mean by energy-like quantity? So we already saw internal energy and enthalpy. But there are more, right? Because look, when we talk about PV system, what do we have? What are the thermodynamic coordinates? We have our pressure, we have our volume, we have temperature, we have entropy, right? Now, first law, you build your first law precisely using this. Right? So if you these are conjugate quantities, and the T and S are conjugate quantities. So you multiply them together, you get your energy. You get a quantity in the energy unit. Okay, so your first law reads du is TdS minus PdV. Okay, this is something I want you to memorize. You don't have to memorize everything, but you have to memorize something in life, and this is the starting point. Okay, but you can ask yourself, well, I don't really that this combine into an energy. Can I choose not to have ds, but I want to have dt? Or can I choose to have dp rather than dv? That is exactly the way to think about this. And you can quickly see that if you think along this line, we will be able to have 4 energy-like quantities, okay, in addition to 2 of them. Okay, and this is how we want to do it. And we usually call this the thermal part. Right? This is obviously related to the temperature, and we call this the mechanical part. Okay, we are going to derive things this way, and later in one of the chapter, I'm going to switch gear quickly to show you I can use all the thermodynamic concept I learned to analyze a rubber band, for example, to analyze a piece of magnet. And what do? I simply change this part, and everything will just follow. Okay, another way to say that is I'm going to look at a different way to perform work on my thermodynamic system. So I change this part and everything else will follow, but the thermal part will remain. Okay. And this energy quantity, energy-like quantity, are very useful, very powerful, and they are useful under different constraints. Okay, so if you have a thermodynamic system which you impose different constraints, and you will be using different thermodynamic, you will be using different energy-like quantity to analyze the problem. You have already seen the parallel between U and H, right? Because U, internal energy, is very easy to understand. If you have a process which does not change the volume, isochloric, okay? And you present this to your friend in chemistry department, they will say, nah, this is difficult to do. I don't want to preserve my volume. I want to just open my beaker to the atmosphere. Okay, then what I have essentially is a constant pressure. That's isobaric, and you can have the parallel here. Okay, in enthalpy. Okay, so keep this in mind. We are going to have different constraints, and you will use it. You use different energy-like quantities. Okay, now let me say the name of this. So this energy-like quantities are called thermodynamic potential. Okay, these are thermodynamic potential. Sometimes people just stop here, potentials, or sometimes some books say would like to complete. They will call this thermodynamic potential functions. Okay, 2 of them are here. The other 2, so you have U, H. The other 2 will be Helmholtz function, F. And the other one, the last one, is Gibbs function, G. Okay, now, if you are with me, this is a piece of warning that you should take it right now. If you pick a different book, check all this symbol. It's very dangerous. I don't like the situation, but I have no power to fix it. Okay. Sometimes internal energy is taking the symbol of E, energy E. That is fine with me. Okay, no problem. Okay, Helmholtz function sometimes is given the notation of A. This is also fine with me. Okay, A, well, it's coming from a German word which I cannot pronounce, A. Gibbs function, sometimes it's given the symbol of F. That is very dangerous. Okay, so there's plenty of opportunities to get confused if you are careless. You pick a book and you start to think F is this F, but actually the whole thing was talking about Gibbs function. Okay, this is one piece of warning. And the second piece of warning is if you pick a book which is not very good, that do not differentiate between Helmholtz function and Gibbs function, and they just call it free energy F, which sometimes they mean Helmholtz, sometimes they mean Gibbs. And that is very dangerous. Okay, so I really, in case those students who miss this lecture does not want to look at the video, I should really write it here. Warning. Different books use different symbol. Now, if I write it this way, maybe it's not strong enough, but please really keep in mind that there's a lot of books out there on thermodynamics written by people with all kinds of different backgrounds. So if you want to read a book, you should really check the notation. Okay, first check the first law, and second, you check this. Okay, let's continue. Okay, internal energy. Internal energy, U, is, what is the natural variable of U? Quick. Okay, you are too slow. Okay, if you look at this, you know, I already mentioned this. U, internal energy, takes the natural variables S and V. Okay, at the end of today's lecture, you will see why this is important. Natural variables, so in this case, S and B are natural variable. Okay, when we look at H, Helmholtz function, Gibbs function, they will have different natural variables. This is another way to motivate you to appreciate this, right? Now, this is fine with me. Okay, H, enthalpy. What is the natural variable? You have S and pressure P. Okay, so here, natural variable. The problem is this: we do not. Entropy is something very abstract from last lecture, you know. And if you want to control this parameter in the lab, that is very difficult. So we want something else instead of S. Okay, so we want, naturally, in the thermal part, we don't have other choice. The natural choice would be T, temperature, for these two. Okay, so here you can already guess. For F, I will tell you the answer before I derive it. So F, what is the natural variable? That will be T. That will take the thermal part will take the temperature, which is great news. Very good. We know how to control this in the lab. And volume V. Okay, so the natural variable is this. Okay, if you know how to control this, you know how to design the experiment to measure the free energy. Okay, and once you know the free energy in terms of the natural variable, you will be able to get everything about the thermodynamic system. That is the point. And last, we have Gibbs function. So Gibbs function, again, you have the thermal part like this and the mechanical part like this. So this is T and P. And Gibbs is particularly important, again, for chemists. Very, very nice. Right? The temperature is, you know how to do that, and pressure, you know how to do that. Okay, another thing which is important for to learn Gibbs, I can give you a preview right away, is we are going to discuss phase transition. Okay, when you take H2O, you get so many phases. So you have something called the phase boundary. You cross the phase boundary, you enter a different phase. And that is usually controlled by temperature and pressure. You go to the mountain, pressure is low. You try to boil your water, the boiling point will be different. Okay, how do you describe this physics? And Gibbs is a particularly useful thermodynamic potential function for that purpose. Okay, so let's define them for you. This is a motivation, if you like. Okay, definition. Definition. Okay, I really mean definition here. Okay, so I define. First, I define my H. Define as U plus PV. This is not new. This is something you have seen before. Okay, the enthalpy is defined this way in terms of the internal energy. You might think this is random, but once you do it yourself, you see this is quite reasonable. Why? Because you see, this is my internal energy, right? I do not want V anymore. I want pressure P. Okay, and how do you get this kind of relation? You do it by looking at the differential change. Okay, so I need to give you the differential change. So I will write dH is du plus pdv plus vdp. Okay, remember my goal is to eliminate the dependence on V. Sorry, I don't want V as my natural variable. Okay, so now that's why I say everybody must remember the first and the second law combined. So this is TdS, this is TdS minus PdV. And then the way you add this term is because you want to kill this minus PdV. This is the way I remember. You can come up with other ways to memorize. That is fine. Okay, so this is the first law, underline for you, and you cancel this. So the end result is TdS plus VdP. Okay? So this then tell me the enthalpy. The natural variable of enthalpy is S and P. Okay. All right. You see, if you remember how to derive, this is just a matter of 1 minute, 2 minutes. Okay, what can I do for to get my Helmholtz function? I want T and V. Any guess? Tell me, how do I define to accomplish that? Hello, hello. What can I do? Don't look at the note. I want you to think, because once you understand from my lecture, you leave my lecture, you don't have to revise too much. Okay, this is a chance to think. I give you time to think. Okay, starting from you, good. Okay, a few students say starting from you, and what do I do? I put this on the same page to help you, right? I already defined H for you. Now what do I do in order to accomplish my goal of having the natural variable to be T and V rather than something else? Okay, this is Mr. Wong, right? This is I need okay, now thank you. This is the way. Okay, indeed, this is the way. And you don't sound very confident. You should just delete that question mark. This is the way. Okay, and then I'm going to do once more, and then okay, I'm going to do it. It's not long. So I have du minus TDS minus SDT, right? This is how I do the differential. Then I use the first law again. I have my TDS minus this, cancel this TDS. Okay, so I'm left with minus PDV and minus SDT. Done. Okay, the thing is, the differential form is very useful. Okay, and okay, I'm going to write first. Be careful of this minus sign that shows up from time to time. Sometimes it's plus, sometimes it's minus. That's why it's better to learn how to derive. Okay. This I don't want to spend too much time now. How do you get G? How do you get your G? In natural variable I want is T and P. Where is your starting point? Now, this is actually an interesting question. I say I don't want to spend too much time, but you can look at this. How do I get it? Again, don't look at the note. Okay, thank you. Some private message came in. More? Do you want to have a chance? Oh, I see a different answer. I see one wrong answer, because that wrong answer is the same as enthalpy. It's not enthalpy, this is Gibbs. Okay. Now, keep thinking, you still have time. So to avoid doubt, this is Helmholtz, this is Gibbs. Okay, what do I want? I want the natural variable to be T and P. So I have two ways to look at this. I wouldn't want to look. I would not want to start from U, right? Because that is too far. I have to change both natural variables, both of them. So I can either start from enthalpy, or I can start from Helmholtz function. Right? If I start from enthalpy, I just have to change the temperature, the thermal part. Okay, so that is the starting point. And if I want to start from Helmholtz, which I'm welcome to do that, I only need to change the mechanical part. So that is this is what I want you to look at. Okay, if I want to start from Helmholtz part, okay, what do I need to do? I need to change this term, right? I do not want PDV. What I really want is VDP. So this looks like here, right? Changing from U to H. So I have an identical process. I will add this. Okay, so some of you got it right. Now the point is mathematics is very simple. I just really want you to think a little bit more, a little bit deeper. Okay, and here I can also say I want to start from H. Okay, why? I want to start from H here, and then I want to change the thermal part. How do I change the thermal part? I have TDS. I want SDT instead, so I have to minus TS. Okay, so try. This will give you the answer. Or sometimes, again, it's not surprising to see people put everything together. If you really insist you want to start from U, welcome, you can start from U, right? Because after all, H can be written as U plus PV minus TS. Okay, and likewise, you can replace this with U minus TS plus PV, same answer. Okay, so this is the way to memorize. Memorize by logical argument, logical reasoning. Okay, I will just skip to the final answer right away. So you have SDT as the thermal part and VDP. Okay, so that is everything about okay, so far so good. Any complaint? Okay. All right, so we have to discuss the meaning of this, but I will do it later. One thing I think which is good to talk about is, I will change the sequence a little bit, okay? So let's add one more. I'm going to give you the important things right away. The important, very important, is Maxwell relation. Relations, actually. Okay, what is this? Maxwell relation. You get a lot of equations today. So I'm going to really present this right now. So these are a set of identity that you can use for you to solve thermodynamic problem very quickly. So first, we need to look at this identity. What are there? I'm going to let me pick Helmholtz to demonstrate. I'm going to write this for you today, but later I'm going to just use F to mean Helmholtz. Okay, for today's lecture, I will just be nice and to make sure we are not talking about different things. Okay, we just derived this. And the differential form is dF is minus PdV minus SDT. Okay? You don't want to stop here. Actually, one thing I should say is all this, so all thermodynamic potentials are function of states. The argument is identical to when we first met enthalpy, right? You look at enthalpy, this is function of state, du, we spend time to prove. P is a function of state, V is a function of state, so the combination is a function of state. And then you just use this argument again and again, then everything, all four thermodynamic potentials are function of states. And now, because they are function of states, you can take advantage of this fact and get more useful stuff, right? And what do you get? Now, first, you look at this. How do you calculate pressure? So you have minus P. Why is minus P in this case? This should not be a problem for you now, okay? So this minus P is partial derivative of F with respect to partial derivative with respect to V at constant T. Okay. There's one question coming, but hold it first. I would like to complete this first, okay? And then minus S, this one by definition is this. Okay? All right, what else can you do? Now, this is what you learned in chapter 1, how to interpret the coefficient in front of dv, how to interpret the coefficient in front of dt. Okay, so this flows naturally. You have this, you go to here, you go to here, you go to here. Okay, but because this is an exact, because f is function of state, df is an exact differential. Okay, I'm not going to write this again and again for all four, so I'm going to show you the full step for one. Okay, and what do you get? The mixed derivative must be the same, right? So here you differentiate first with respect to v. Now the second derivative you will differentiate with respect to t. So you differentiate this with respect to t at constant v. Okay, this mixed derivative must be the same. Okay, so what is the other side? You already differentiate with respect to t, and now you differentiate again with respect to v, and you keep t constant. Okay, let's tidy up a little bit. So this is the first one of the it's not really the first, one of the four Maxwell relation. So just get the minus sign out. Okay, and then you can do a lot of things. Sometimes you can take the reciprocal, and this will be a partial v, partial s, and here will be a partial t with partial derivative of t with respect to p. You can have all kind of combination like this. Okay, and this is when some students begin to get upset. Suddenly, after one slide, you get so many equations. How do you handle? Right? So anyway, before talking about your emotion, let's present everything. So this is the Maxwell relation based on F. So you can repeat the rest. You should do that because, as I say, I do not encourage memorization here. You should do it so you know how to get this. Okay, so I'm going to give you the result based on you. What do you get? You have partial t, partial v, constant s. Okay. Now here, there's a minus sign. This is something I can never remember. Sometimes it's minus, sometimes it's not. So really, I really want to say this again. Don't memorize. And then based on age, you have this. And then finally, based on G, you have this. Okay, so maybe one thing I can, sorry, I don't like this. Here, I want to bring this minus sign out. Maybe one thing you can pay attention is the following. You see, you always have, if you look at, if you draw a cross, you will see whenever you have t at the bottom, you have s at the top on the other side. So this multiply to become ts, this is pv. Right? So you have pv, you have ts, you have pv, you have ts, pv, ts. Okay, and then at least this is a pattern you should observe. And then the minus sign, you can come up with a way to memorize if you wish. But again, let me encourage you not to memorize too much. Okay, and why do we want this? Look at let's just look at the first one. You will see why this is good. If I want to ask myself, what is this derivative? This is a difficult one to even imagine, right? The change of entropy as a function of volume, right? This partial derivative basically means this. It's so difficult to imagine. But good news, what is this? This is actually nothing but the change of pressure when I vary the temperature. Okay, so this is again useful for extracting information about the thermodynamic system by relating to some partial derivatives that can be controlled easily in the lab. Okay. How tired are you? Okay. Can we just have a very short break because I have plenty to talk about. Now it's 12:26, 12:30. I want to pick up and give you some more equations. But I think you are going to like it. I'm going to present something additional, which is not in the note, just for you, for your amusement. Okay, so let's take a quick break and come back again. So 12:30, so long enough for you to go to toilet. Okay, this is an aside. So let me, this is an aside. I include here because last year, student told me the way you define all these thermodynamic potentials are very random. You just seems to just add something like this. Okay, but I actually disagree because now I know this is not random because you can get it systematically. Okay, so this is the purpose. I want to spend a bit of time quickly to convince you that this is not as random as you might have thought. Okay, so we can systematically write down all this systematically write down the thermodynamic potentials. How? By viewing the process as the Legendre transformation. Have you seen this before in other courses? The transformation itself? You should have seen something like this. But you probably don't think about it this way here. Yes or no? I just want some yes/no question, then that will make me happy. Good. Okay, then I can go a bit faster. Okay, the background is this. Background. I'm going to, okay, but not familiar. Okay, fine. You get it. Don't worry. Don't worry. Okay, so I'm going to use some symbols. They are not more general first. Okay, so I'm going to look at this. I'm going to look at a function of two variables, z, capital, as a function of little x and little y. Okay, I try to write it for the little one. I really try to make it small and write it a little bit more curved. Okay, so in this case, I will have d capital Z. Now this x is my natural variable. So let me write it like this. plus dy. And the conjugate pair, which is useful for us, I'm going to write it in terms of capital X and capital Y. Okay, so X are conjugate pair. Conjugate pairs. And then y, big Y and little y are also. Okay. Now, what do we want? What we want instead is some other function x, and I want it as a function. I want to keep the first variable, but I want to change it to big Y instead. So I want to use the conjugate variable of little y, which is big Y, instead. Okay, so this is related to T, the relationship between T and S, P and B. Okay, so we're given this, we are given Z, and we want this instead. Okay, here's the clamp. So the transformation, we can transform by this. So I'm going to write n x y. Okay, this is related to z x y minus y times big Y. This is what you have done. Okay, but what you have done is actually very precise. This is related to this transformation, Legendre transformation. Right? You have done something like this, but you probably didn't question it much. Okay, so you know, in this case, this will give you the desired dn. So dn will be dz minus y d big Y minus big Y d little y. Okay, so the end result, once I plug this in, I will have x remain the same. I don't want to change. And y dy will cancel with this, and this is y dy. As required. This is as required. Okay, at this point, I just change a symbol, make it very generalized, and then you can just keep repeating this process, right? Once you change one, you can change the other one. Then you get everything. So the question then is to understand this equation. Why can you write it like this? This one. Why? Otherwise, if we don't understand this, you can still make the same complaint. We do not have any new insight. Okay, now this is the juice of this discussion. This is, you can view it like this. Okay, why do we have this? So I'm going to, and then erase the rest. The next 5 minutes, we want to understand why we can do it like this. Okay, the reason is this. You can look at a curve. It's very artistic, but I don't like. You can look at a curve given as in the space of this coordinate system, big Z and little y. And how do you draw a curve? There are a few ways to draw the curve. You can you can draw the curve by a lot of points, right? So that is to say, if I give you the coordinate y and z, you can put a point. I give you another one, you put a point, and this will give you a curve. So this is called the point geometry. So this z, y, this is a geometry problem. This is a point geometry to give a trace. of a curve. Okay, the other way you can look at this is to look at a set of lines, right? You can, I want to draw it very carefully, so I can draw a straight line. I can draw a straight line. Another one. These are really straight lines, okay? These, if I have a lot of lines, I can think of my curve as formed by the tangent of the lines, right? So if I have a curve, let's say I have a curve, how do I form the curve? I can specify the point, or I can specify the tangent for all these points, and I draw all these tangents, they will give me the curve. So this is called the line geometry. Okay, so this is point geometry. So essentially, this is a transformation from point geometry to line geometry. Okay, so the N, big N, so N is the line geometry. You will see how to specify this soon. This is the line geometry. This transformation to big Y is a line geometry to give the trace of the same curve. That is to say, you are looking at the same curve, but you choose to describe it differently. And that is why you have this transformation. Okay, so my remaining goal is to give you this equation, then I'm done. Okay, so I'm going to look at a point. I'm going to look at a particular point. Let's say this point here. Okay, this is the point with a coordinate y, a general with some coordinate y, some coordinate z. And I'm going to define the intercept for this particular line, this one, as n. So this is the one I choose to analyze. Okay, so the z-intercept is n, and the slope of this line you know how to describe, right? So it's a straight line, so you know how to describe the slope of this line. So the slope of this line will be the value of z. Slope will be z minus n, so the value of z minus the intercept, divided by the y value minus the coordinate of this intercept, which is by definition 0. Okay. And what is this slope here? This slope is the slope of the line, right? This slope of the tangent. For the line crossing this point z, y. Okay, and this is my slope y, and this y will just be d z d y. Right, this is the slope. Okay, and slope can be expressed by simple argument by looking at the point. Okay, so I rearrange, I will get this equation. I will get my n is z minus y times big Y as required, exactly written here. As claimed. Okay, so after that, everything is familiar. This is, you can change change all this symbol to thermodynamic variables. You'll be able to get the result we presented earlier. Okay, so I'm not going to ask you this in the exam. I just want to convince you that this is not as random. This process of introducing 4 thermodynamic potential is very robust. It's not something as random as some students might claim. Okay, next we want to go back to discuss all 4 thermodynamic potential. In particular, what's the meaning of this? How do you understand this? If you have a certain constraint, what is the information you can extract from this? Okay, so the easiest one is U, internal energy U, because you have seen many times. You already know the result. So let's write very quickly. This is the first law and the second law combined. And once you know U as a function of S and V, you know how to calculate the rest, because T can be obtained by partial derivative. If you know U as a function of S, then you know how to take derivative. And that will give you your temperature, and then pressure as well. You have a minus. Okay, and then you can go on and do the Maxwell. I don't want to do that. Okay, but what is the interpretation? One interpretation that's easiest is if you have an isochoric process. This is a very standard way to understand internal energy. How do you get internal energy? Suppose you are able to design your experiment. You want to do it in a way that gives you the internal energy. Okay, then if I have the power to design the experiment, I will demand my dV to be 0. I'm not saying this is easy, but I can demand this. So in this case, I will have du is given only by TdS. Okay, now I can only stop here in the most general argument. But if I'm able to design my experiment such that this process is reversible, right? So this is an additional constraint. If I'm able to demand further that this process can be made reversible, I can do it as slowly as possible. I can have very well controlled parameters to do it. Then I have something more. My du can be written as TdS reversible. If this is reversible, then this will be d bar q reversible and constant pressure. Okay, and that will give me the heat capacity at constant volume times dt. Okay, now at this point, it's worth mentioning this. Now this du equals Cv plus times dt. We saw it before, and then we saw it in a context that I gave you a huge warning. Okay, I told you that was only true. You can write it right away if you have a ideal gas. You saw this much. Okay, and this is a point where I need to I can come back to this point. This is actually educational. Look, if you just write this without all this reasoning, you are so wrong, right? The fact that we can write it this way relies on isochoric process, reversible. There are a change of argument that you need to include. But for the ideal gas, you directly write this. Okay? All right, so now in this case, if you have all these conditions, delta U can be calculated if you know the temperature, if you know the experiment condition well enough for you to give the process, the range of the temperature for the process. Okay. All right, so this is how you can get the change of the internal energy by measuring the heat capacity as a function of temperature. Okay, then you can find your internal energy change. So the interpretation for U is such that the internal energy is useful when you discuss the change in an isochoric reversible process. Okay, so this is energy change due to heat flow, due to this, in an isochoric reversible process. Okay, so this is what you find in the textbooks. In Blundell and Blundell, in Atkins, you will find this statement. Okay, you can, from here, I think you can immediately guess what is DH. For you, this should be fast. You just change isochoric to isobaric, and everything you keep, and that will be DH, a change of enthalpy. Okay. But with the enthalpy, let me see. For the enthalpy, maybe give me one more star here. This is now we are talking about enthalpy. So you will have this. Everything is parallel. So here you can have integrate. If you know how to measure heat capacity at constant pressure, this is the expression. Okay, and this is important because this is the experimental condition that many people are comfortable with. To keep the pressure constant is as easy as just opening your experiment to the surrounding, to the atmosphere. So that will maintain. The atmosphere is so much bigger, so you maintain the constant pressure environment. Okay, so these are easy pieces, I would say. Now, we want to look at the other two. What do I mean by those? So I will start from Helmholtz function. And just to remind you, this F is U minus TS. Okay, so dF will be minus S dt P dV. Okay, and then S is this partial derivative. Okay, and you can do Maxwell, but I don't want to worry about this. Now, here, usually when you discuss Helmholtz function, in many books, eventually the discussion is related to the work. How much work you can extract from the system, right? And therefore, this is also given the name of free energy. Why is it a free energy? Why is it free? Okay, so let's start by looking at this term again. If you want to discuss the work done, the easiest is to first look at design your experiment in an isothermal way. Okay, in this case, you get your dF is minus P dV. Okay, so your delta F will be V1 to V2 P dV. Okay, but what is this minus PdV? Can we say something similar to the way we discuss internal energy and enthalpy? Yes, I think at this point you should also pay attention on this, right? We want to also look at the case when we have reversible. Right? When you have a reversible work, okay, so if you have work performed on the system, so work done, on the system reversibly. So this is on the system. On the system, then the work done is by the surrounding. Okay, on the system, then by the surrounding, you get this minus sign here. Okay, so in this case, we know d bar W reversible will be minus PdV. Okay, so this is okay, I think. So what can we say next? If you have f, what is this Helmholtz function f? If you have a reversible work done, so for a work done on the system reversibly, then f you can increase the Helmholtz function. Right? This minus sign really means this. So if I do work on the system, that's to say I take my PV system, I compress it, I perform work on the system, then my Helmholtz function will increase, and this is the meaning of this. Okay, more generally, what happens is this. If what the statement, I will write you the statement. So here, we want to understand why we also call this Helmholtz function the free energy. Which part is free? So if you have a decrease, so more generally, if you look at the system, if you look at your thermodynamic system, and you find that the Helmholtz function decrease. Okay, and what is this decrease? The F drops by some amount after a certain time. You find this drop in F, and in fact, this has a straightforward interpretation. So this drop, the decrease in F, is the same as the maximum energy that can be free. But what is the constraint? That can be free in an isothermal process and made available for work, for useful work. Okay, try to appreciate this. If I have a decrease in F, suppose I have an isothermal process. I monitor my Helmholtz function, and I find that this Helmholtz function is changing in time, but it's an isothermal process. But this amount this amount of F drops is actually the maximum energy that can be free, can be reused, can be extracted to do useful work. Okay, and that is, in this sense, this is the amount that is freely available for you to extract work. And that's why this is also called Helmholtz free energy. And you might also feel that this kind of statement is a little bit, it might ring the bell, right? You have seen something similar in mechanics. right? Imagine you have a spring, right? You compress it, okay? And later you want to extract work out from this. So this is a bit like you are storing this amount of energy that you want to use for work in the spring, right? So in the case of spring, you call this the elastic potential energy. So in the case of thermodynamics, we call this the thermodynamic potential. That is why there's another way to look at this. Why do we call this the thermodynamic potential function? That's because later we want to be able to retrieve this for useful work. Okay, so I want to write a little bit more here to sharpen this argument for you. Okay, I'm going to consider a system. I'm going to consider a system. This system can exchange energy with the surrounding. Okay, consider a system that can exchange energy with the surrounding. Okay, this is my universe. Right? I have a system, I have a surrounding that can exchange energy and nothing else. Okay, so according to my knowledge of the second law, the entropy of the universe cannot decrease. So actually I want to write more at a fixed temperature. T. Okay, isothermal. So the second law will demand this: the change of entropy for the system plus the change of entropy for the surrounding, the total has to be greater or equal to 0. So this comes back to the matters arising at the beginning. If I do not close my system, you really cannot say too much about the change of S. It can go up, it can go down, fine, no problem, no violation. But once I close it, the entropy change of the universe can only increase, or stay constant, cannot decrease. Okay, so this 0 here means the surrounding. So this is the surrounding. Okay, now I'm going to suppose some heat enter the system from the surrounding. Here. Okay, so this is d bar q. Just let me consider a tiny amount of heat enters the system. So in this case, the entropy of the surrounding will change according to this. Now, heat enters the system, so d bar q leaves the surrounding. I have to put a minus sign. And this happens at the temperature T. Okay? So if I use the second law would then tell me ds minus this amount is minus, okay, let me write this. Minus this amount has to be greater than 0. Okay, so this is, now all the symbol must be very carefully considered. Okay, so this is what I meant. I do not use equality, I use the most general case for you. Okay, so this is the amount of heat enter the system, and ds is the entropy change of the system. 0 is the surrounding. Okay, now I apply the first law, so d bar q. So this is first law, is du minus d bar omega, d bar w. Maybe I said omega before. Sorry, in that case, from the first law. I apply the first law for the system. For system. Okay. Okay, what can I write more? So I have du minus d bar w is the same as this. I look at the system now. This system acquire this heat from the surrounding, and because of this, I have to satisfy some inequality like this. Okay, so now I link all this argument together. The rest is just mathematics. I can then have this. I move this over there and move d bar w to the right hand side. You might be, you might already guess what I want to do. What I want to do is to try to recast this into a formula which directly gives you the Helmholtz function. And I'm nearly there, I'm nearly successful. Okay, for the fixed temperature isothermal process, I can then put this T into the differential, right? This is isothermal, okay, isothermal. Okay, then I will have U minus Ts is less than d bar W. Okay, then I get the result I want. This is the change of this U minus Ts is my definition of F. I don't want to go back, you have to trust me. So this is my definition of F. You have again seen something similar when we do the enthalpy. Now I repeat the same trick to get the expression for F. Okay, and this is the interpretation about this work, the amount of energy, if dF drop, how much energy I can recover for useful work. And this is the way to look at it. Okay, you use a second law. All right, so let's bring this up a little bit and write down the interpretation. So the interpretation here. Let's don't be lazy and really write down all the keyword. So what does it? What is the interpretation for all this argument? Okay, here we go. If the process is reversible and isothermal, the work done on the system equal. Now, this is reversible and isothermal. I will have equal sign, and this is equal to the increase in F. Okay, so this argument is very general. If you have a reversible system, you would just drop the inequality, you will get to this point and you get to this result. Okay, and then that is why this is called the free energy. Okay, where do you store the energy? You store the energy. Just think about this problem about this elastic, the spring problem I mentioned earlier. If you have reversible process, you want to store your energy somewhere and then use it later, right? And this energy store. So the store energy. Just think about that spring analog. So you store the energy where? You store it in the system, in systems Helmholtz function. And this store energy, the point is this store energy can be retrieved for useful work, can be retrieved for useful work later. So it's like the potential energy of the mechanical system. Okay, now this is a reversible process. What if the process is not reversible, not quasi-static? So for non-reversible, but I don't want to complicate the system, but I still want to discuss the isothermal case. So sorry, to help you revise, I write a bit more for you for the reversible, but for non-reversible, but still isothermal. What we will have up there, this will be the case. So we will have D bar W is greater than dF. Okay, so I would just say in word, the work done on the system is only partially converted into the change of the free energy of the system. And why is the other part? The other part will be wasted through some heat flow, heat transfer to the environment. It's a bit like friction. Okay, we can do the same with Gibbs energy, Gibbs function, and that is something I will do next time. But now, in the remaining few minutes, I want to come back to the point about this full knowledge of the thermodynamic system. So full knowledge about thermodynamic system. Okay, so this is also discussed in the heading of Gibbs-Helmholtz equation. Actually, if you read Blundell and Blundell, it's equation. So the book treats several equations together and with the same form. They call them, the book called this equation the Gibbs-Helmholtz equations. Okay, so this is related to the fact that if I know the thermodynamic potential given explicitly in the natural variables, I know everything. I have the complete information about the thermodynamic system. Okay, this will lead to a few equations, and these equations are Gibbs-Helmholtz. Okay, so again, I'm going to take F as the example, Helmholtz function as the example, as demonstration. And in the assignment, I'm going to give you the more difficult case. I'm going to give you the thermodynamic potential not in the natural variable, and you will see to get the full information, you have a lot more work to do. Okay, and in fact, this is part of the assignment. You have chance to practice. Okay, what is the natural variable for F? This is T and V. Okay, so suppose you know F in terms of T and V. Okay, so you immediately know your entropy. This I already wrote. And you also know pressure. So you know a lot already, right? If I say you know F in terms of T and V, you better know T and V. That's to say, you have control for T, you have control, you know how to control volume. And after you control these two, you know how to calculate F. Okay, so that is the input, you know this much. Then you ask yourself, oh, do I know the entropy? Yes, you actually know because you know this function, you can do partial derivative. Do I know the pressure at any given point of T coordinate TV? Yes, you know because you can also do this partial derivative. But that is not enough. By full information, I mean you also know everything else. You know all four thermodynamic potential functions. How do you know U? You know it because U is written as F plus TS. You know F, right? Because I already said you know F. You know T. And you know how to calculate S. Okay, let's plug it in. You have F. There's a minus sign, so I change to minus. So this is TS, partial F, partial T. Okay, and again, you know how to calculate U because you know F as a function of TV, so you know how to calculate this. Everything is known. Okay, up to this point is easy, but if you have not seen this before, this is a bit hard. You can write this in a more compact form. This is in fact this function. Now, how do you prove it? The easiest way is to take the derivative and you come back to here. That's why I say if you haven't seen a function like this, not in this course, not in other mathematics course, it might not be easy for you to guess this form. But I'm telling you this is correct. Okay, you should practice this. It's very common for this part of the course to write things like this in a very compact form. So if you know how do you calculate U? If you know your F, you take the thermal derivative of this ratio, then you get your internal energy. But that is not enough. Do you know Gibbs? Do you know Gibbs? You can try. How do you do that? Gibbs energy is F plus PV, right? So this is identical to this form. So I will have my F, which I know, and I have the P, which is so P is here, and V is what I know. I know how to control. So I have this again. Sorry, am I right? Yes. Okay, you compare these two forms, you will see that now you recognize these are same structure, mathematical structure. So in fact, this can indeed be written in a very compact form. Okay, and finally, if you know U, you know F, you know G, it's not surprising that you know the enthalpy. I will just give you the result. So H is again in a form that looks like this. This is, you can fill in the gap yourself. This will give you T squared. This is G over T. Okay, but first you need to calculate the G. Sorry, this is, H is written like this. But here from this line, you know how to calculate G. After you calculate the G, you can take this ratio, you can calculate your H, the enthalpy. Okay, so this is what I meant by the full knowledge, and this is called the Gibbs-Helmholtz equation. Okay. That's what I want to say today. Next lecture, we are going to talk about something a little bit more abstract. We are going to introduce thermodynamic equilibrium and the concept of availability. This is another quantity. This is availability. A symbol is A. That's why another reason why I want to reserve the symbol A for availability rather than for Helmholtz. Okay, so next lecture we will finish this, and we are going to talk about, to give you 3 more equations. Again, more toolbox, more tools in the toolbox, and those are called the TDS equation, TDS equations. So this is the next lecture. And then you can have a very happy New Year. Okay, thank you very much. See you on Wednesday.